Welcome! In today's session, we'll be tackling the problem number 2115, find all possible recipes from given supplies. This problem is an intriguing blend of graph traversal and dependency resolution. Let's dive in and explore the different approaches to solve this challenge. In this problem, you are tasked with determining which recipes can be prepared based on the ingredients and supplies available to you. You are given a list of recipes, where each recipe is represented as a string, and a corresponding list of ingredients needed to prepare each recipe. Additionally, you have an initial list of supplies, which are the ingredients you currently have. The challenge is to figure out which recipes can be made using these supplies or by using other recipes as ingredients. Each ingredient is uniquely represented by a string, and recipes can be interdependent, meaning a recipe may require another recipe as one of its ingredients. As you successfully prepare recipes, they are added to your supplies, enabling you to possibly make more recipes. The goal is to return a list of all the recipes you can prepare, in any order. The output of the problem is a list of strings representing the names of the recipes that can be prepared. The order of the recipes in the output does not matter. Let's look at an example to clarify. Suppose you have one recipe, bread, which needs two ingredients, flour and water. Your initial supplies include flour, water, and yeast. Since flour and water are both in your supplies, you can prepare bread. Therefore, the output for this input would be a list containing just the recipe bread. In this example, we expand the problem to include two recipes, bread and sandwich. The bread recipe requires flour and water, while the sandwich recipe requires bread and ham. The initial supplies include flour, water, and ham. First, bread can be prepared because its ingredients, flour and water, are in the supplies. Once bread is prepared, it becomes part of the supplies, which now include flour, water, ham, and the newly prepared bread. This allows sandwich to be prepared, as both of its ingredients, bread and ham, are now available. The output in this case would be a list containing both bread and sandwich. Here's another example, where we add a third recipe, salad, to the list. The salad recipe requires lettuce and tomato, both of which are already in the initial supplies. Similarly, bread can be prepared because its ingredients, flour and water, are in the supplies. Once bread is added to the supplies, sandwich can also be prepared because its ingredients, bread and ham, are now available. In this scenario, all three recipes bread, sandwich, and salad can be prepared, so the output will include all of them. To summarize, once a recipe is prepared, it gets added to your supplies, enabling the preparation of other recipes that depend on it. However, there are constraints and edge cases to consider. For instance, the number of recipes and ingredients is capped at 100, and the length of each string is limited to 10 characters. Additionally, all strings are distinct and consist only of lowercase English letters. Some important edge cases include handling circular dependencies, where a recipe indirectly depends on itself, or cases where no combination of supplies can fulfill a recipe's ingredient requirements. Recipes with no ingredients can always be prepared, and disconnected recipes should be handled independently. By addressing these constraints and edge cases, you can ensure that your solution works for all possible inputs. To tackle this problem, the first approach we might consider is a brute force solution. The intuition here is straightforward. We aim to repeatedly check whether a recipe can be made using the current supplies or other recipes that have already been produced. To do this, we start by placing all the given supplies into a set. Then, for each recipe, we verify if all its ingredients are either in this supply set or can be made from other recipes. If a recipe meets this condition, we add it to the supply set and continue the process until no more recipes can be added. While simple to understand, this approach comes with significant trade-offs. Its time complexity can be high because we repeatedly check all recipes, and the space complexity grows with the number of recipes and supplies. Additionally, this method struggles with cyclic dependencies, which can lead to infinite loops. These limitations make it inefficient for larger input sizes or complex scenarios. A more systematic and efficient solution involves modeling the problem as a graph and using topological sorting, specifically Kahn's algorithm. In this graph, nodes represent the recipes and supplies, while directed edges denote the dependencies, essentially, an ingredient pointing to the recipes it's required for. Using this structure, we can determine the order in which recipes can be prepared. The process begins by constructing the graph and calculating the in-degree for each node, which represents the number of dependencies for each recipe. Next, all supplies, which naturally have an in-degree of 0, are added to a queue. As we process the nodes in the queue, we reduce the in-degree of their dependent recipes. If a recipe's in-degree reaches 0, it means all its dependencies are resolved, and it can be added to the queue. At the end of this process, the nodes that have been processed represent the recipes that can be successfully made. The topological sort approach brings significant improvements in efficiency and robustness. Its time complexity is proportional to the sum of the nodes and edges in the graph, which corresponds to the number of recipes and the total number of dependencies. The space complexity is also manageable, requiring storage for the graph and in-degree data. Importantly, this method guarantees correctness. It can detect cycles in the graph, which indicate invalid dependencies, something the brute force approach struggles with. These advantages make it a clear choice for large datasets. Additionally, by representing the problem as a dependency graph, we avoid redundant checks. Recipes with fewer or no dependencies can be resolved first, perfectly aligning with the principles of topological sorting. This efficiency and clarity were key reasons for selecting this approach as the preferred strategy. The key insight that unlocked this solution was recognizing the analogy between this problem and task scheduling with dependencies. Once framed in terms of graph theory, applying topological sorting provided a clean and systematic way to handle even the most complex cases. While this approach is slightly more complex to implement than brute force, the trade-offs are worth it. It efficiently handles edge cases, like cycles and dependencies, and avoids redundant work, ensuring an optimized solution. By leveraging the graph structure, we can clearly determine the order in which recipes can be made. In conclusion, topological sorting stands out as the optimal choice for solving this problem due to its balance of efficiency, clarity, and robustness. To solve this problem, we need to determine which recipes can be created using a given set of initial supplies, considering that some ingredients are themselves recipes that need to be prepared first. A brute force approach to tackle this involves repeatedly checking each recipe against the current set of available supplies. If all ingredients for a recipe are available either as initial supplies or as recipes that have already been created, we add that recipe to the supplies. This process continues until we reach a point where no new recipes can be made. First, we initialize the supplies as a set for efficient lookups, since checking membership in a set has an average time complexity of 1. We also track the recipes that need to be processed and maintain a flag to check if progress is made during each iteration. This flag helps us determine when the loop should terminate, ensuring we don't perform unnecessary checks once no new recipes are possible. Now, during each iteration, we process the list of recipes. For each recipe, we verify whether all its required ingredients are present in the supplies set. If they are, we add the recipe to the supplies and mark it as completed. After evaluating all the recipes in the current iteration, we remove the completed recipes from the list. This cleanup step ensures that recipes already added to the supplies are not repeatedly checked, which saves computational resources. If no new recipes are added to the supplies during an iteration, the progress flag remains false, and we terminate the loop. Finally, we return a list of all the recipes that were successfully added to the supplies, which represents the recipes that can actually be made using the given ingredients and their dependencies. The pseudocode provided shows the implementation of this brute force approach. We start by converting the initial supplies into a set for efficient lookups. The remaining _recipes set holds all the recipes yet to be processed. For each recipe, we check whether all its ingredients are present in the supplies. When a recipe is added to the supplies, we also update the progress made flag to true and add the recipe to a temporary list for removal. After processing, completed recipes are removed from remaining _recipes, ensuring that only recipes still requiring evaluation remain. If no progress is made during an iteration, the loop breaks, signaling that no further recipes can be created. The final result is a list of recipes that were successfully added to the supplies. Using a set for supplies is critical because it optimizes ingredient lookups to 1 on average, which is a frequent operation in this algorithm. Iterating until no new recipes can be made ensures that dependencies are resolved, even in cases where recipes depend on other recipes. For example, if recipe A relies on recipe B, which in turn depends on recipe C, this iterative approach ensures that recipe C is processed first, followed by recipe B, and finally recipe A. Removing completed recipes from the list reduces the number of recipes that need to be checked in future iterations, improving efficiency. Regarding complexity, the worst-case time complexity is O, R*n*k, where R is the number of recipes, N is the average number of ingredients per recipe, and K is the number of iterations before no progress is made. The space complexity is O, R plus S, accounting for the supplies set and the storage of remaining recipes. Certain edge cases must be considered. Recipes with circular dependencies, where two or more recipes depend on each other, cannot be completed and will remain in the set of unprocessed recipes. Similarly, recipes that require ingredients not present in the initial supplies or other recipes will also remain incomplete. If no recipes or supplies are provided, the output should be an empty list. To optimize the brute force approach, we can use a topological sort by representing recipes and their dependencies as a directed graph. This allows us to process recipes in the order of their dependencies, avoiding redundant checks. Alternatively, using an in-degree count for each recipe and processing recipes with no unmet dependencies in a queue can further reduce redundant operations, resulting in a more efficient solution. Here, we start by importing the necessary modules, defaultDict and Deque, to help us manage the graph structure and the queue for processing. Then, we define the findAllRecipes method, which takes recipes, ingredients, and supplies as input. First, we initialize two data structures, graph, to represent dependencies between ingredients and recipes, and in_degree, to track the number of prerequisites for each recipe. Next, we populate these structures by iterating over each recipe and its corresponding list of ingredients. For every ingredient required by a recipe, we add the recipe to the adjacency list of that ingredient in the graph. Simultaneously, we increment the in-degree of the recipe to reflect the number of ingredients it depends on. After building the graph, we initialize a queue with all the available supplies, which are the ingredients we already have on hand. We also create an empty set, possible_recipes, to store the recipes we can successfully make. Finally, we start processing the queue. While there are items in the queue, we dequeue the current ingredient or supply and examine its neighbors in the graph. These neighbors represent recipes that depend on the current ingredient. For each of these neighbors, we reduce their in-degree by 1, as we've now accounted for one of their required ingredients. If the in-degree of a neighbor becomes 0, it means all its prerequisites are satisfied, so we add it to the queue for further processing. Additionally, if the neighbor is a recipe, we add it to the possible_recipes set, since it's now feasible to make. After the queue has been fully processed and no more dependencies remain, we return the possible_recipes set as a list. This ensures that we only include recipes that can be made with the initial supplies and any other recipes that become feasible as we go through the dependencies. This approach effectively uses topological sorting to determine which recipes are achievable, ensuring an efficient and systematic solution to the problem. Here, we start by defining our method findAllRecipes, which takes 3 parameters: an array of recipes, a list of lists representing the ingredients required for each recipe, and an array of supplies that are initially available. The goal is to determine which recipes can be created using the given supplies and other recipes as ingredients. To achieve this, we use a graph to represent dependencies between ingredients and recipes, and an in-degree map to keep track of how many dependencies each recipe has. First, we initialize the in-degree map by setting the in-degree of all recipes to 0. Then, we iterate over the recipes and their respective ingredients to build the graph. For every recipe, we add edges from its ingredients to the recipe itself and increment the in-degree of the recipe by the number of its dependencies. This sets up the relationships between ingredients and recipes, where the ingredients act as the prerequisites for the recipes. Finally, we create a queue to store supplies, which will serve as the starting points for our traversal. At this stage, we are ready to begin processing the graph. All the initial supplies are added to the queue because they are available without any prerequisites. From here, we use breadth-first search, or BFS, to traverse the graph. While the queue is not empty, we process each item, starting with the current supply at the front of the queue. For every supply, we check its neighbors in the graph. These neighbors represent the recipes that depend on the current supply. For each neighbor, we decrement its indegree to reflect the fact that one of its dependencies has been processed. If a neighbor's indegree becomes 0, it means all its dependencies have been satisfied, so we add it to the queue for further processing. Additionally, if this neighbor is a recipe, we add it to our set of possible recipes, indicating that it can now be made. This process continues until the queue is empty, ensuring that all recipes and their dependencies are evaluated correctly. By the end of this traversal, we will have determined all recipes that can be created using the given supplies and other recipes as ingredients. Finally, we convert the set of possible recipes into a list and return it as the result. The use of a set ensures that each recipe appears only once in the output, even if it can be derived through multiple paths. This implementation effectively combines graph traversal with indegree tracking to solve the problem in a structured and efficient manner. By leveraging the initial supplies and processing dependencies in a step-by-step manner, we ensure that only valid recipes are included in the result. This completes the implementation of the solution. In this basic example, we are tasked with making the recipe bread using the ingredients flour and water, which are already available in our supplies. First, we construct a graph and an indegree map. The graph represents the relationships between ingredients and recipes. Flour and water lead to bread. The indegree of bread is 2, indicating it depends on 2 ingredients. Next, we initialize a queue with the supplies, which are flour and water, as these are immediately usable. During the queue processing, we first take flour out of the queue, reducing bread's indegree to 1. Then, we process water, reducing bread's indegree to 0, meaning bread can now be made. At this point, we add bread to both the queue and the list of possible recipes. After processing all items in the queue, the final state shows that bread is added to the set of possible recipes. The output for this example is simply bread. Now, let's consider a more complex scenario involving multiple recipes. In this new example, we have 2 recipes, bread and sandwich. Bread requires flour and water, while sandwich depends on bread and meat. The supplies include flour, water, and meat. For this example, we start by building the graph and indegree map. The graph shows that flour and water contribute to bread, while bread and meat contribute to sandwich. The indegree map reflects these dependencies. Bread has 2 and sandwich also has 2. The initial queue contains the available supplies, flour, water, and meat. As we process the queue, flour is dequeued first, reducing bread's indegree to 1. Then, water is dequeued next, reducing bread's indegree to 0. Since bread can now be made, it is added to the queue and the list of possible recipes. Next, meat is dequeued, which reduces sandwich's indegree to 1. Finally, bread is dequeued, reducing sandwich's indegree to 0. With sandwich now makeable, it is added to the queue and the list of possible recipes. Once the queue is fully processed, the final state reveals that both bread and sandwich can be made. The output for this example is bread, sandwich. Now, let's examine a case where a recipe cannot be made due to missing ingredients. In this example, we are trying to make cake, which requires flour, sugar, and eggs. However, the available supplies only include flour and sugar. Here, we construct the graph and indegree map. Flour, sugar, and eggs all lead to cake, giving cake an indegree of 3. The queue is initialized with the supplies flour and sugar. As the queue is processed, flour is dequeued first, reducing cake's indegree to 2. Then, sugar is dequeued, reducing cake's indegree to 1. However, since eggs are missing, cake's indegree never reaches 0, meaning it cannot be made. The final state shows no possible recipes, and the output is an empty list. Here, we begin analyzing the time complexity of the solution to the problem. First, we consider the graph construction step. For every recipe in the list of recipes, which we denote as R, we iterate through its list of ingredients. The total number of unique ingredients across all recipes is represented as N. For each ingredient in a recipe, we perform constant-time operations, such as adding edges to the adjacency list and updating the indegree dictionary. Summing this over all recipes gives us a total cost proportional to the number of ingredient recipe pairs, which we denote as E. In essence, this step of graph construction has a total time complexity of O(E), where E is calculated as the sum of the lengths of all ingredient lists across the recipes. Next, we analyze the time complexity of processing the queue. The queue is initialized with all initial supplies, denoted as S. Each supply from the queue is processed only once. For every supply, we visit its neighbors in the graph, which represent recipes that depend on this supply. The total number of neighbors processed is bounded by E, the total number of edges in the graph. This means the cost of processing the queue is proportional to O(V) plus E, where V represents the total number of nodes, which is the sum of supplies and recipes, or S plus R. Combining this with the graph construction step, the overall time complexity of the solution becomes O(V) plus E, as the two steps are additive in their computational cost. Now, let's focus on the space complexity. The solution uses several data structures whose space requirements we need to account for. First, the adjacency list representation of the graph requires space proportional to the number of edges, or O(E). Then, the in-degree dictionary, which tracks the number of dependencies for each recipe, requires space proportional to the number of recipes, or O(R). The queue, which temporarily holds nodes during processing, can hold up to V nodes in the worst case, where V equals S plus R, so its space complexity is O(V). Additionally, the set used to store possible recipes has a space requirement of O(R), as it contains at most all the recipes. Altogether, these components dominate the space usage, leading to an overall space complexity of O(V) plus E. We also consider additional memory usage. Temporary variables and loop counters require negligible space, so they don't significantly impact the overall complexity. Thus, the dominant space usage comes from the graph and the queue, confirming that the total space complexity is O(V) plus E. Moving on to the best, average, and worst case analyses, in the best case, all recipes are directly achievable from the initial supplies. Here, while the graph still needs to be built, queue processing is minimal, resulting in the same O(V) plus E complexity but with lower constants. In the average case, recipes have dependencies that require moderate graph traversal, still maintaining O(V) plus E. In the worst case, recipes depend heavily on each other, requiring a full traversal of the graph. Even in this case, the time complexity remains O(V) plus E, though the constant factors may increase due to deeper traversal. Let's compare this graph-based approach to a brute force or naive method. In a naive solution, we might repeatedly check each recipe's ingredients against the current list of supplies. This involves nested loops, where we iterate through all recipes and then through their ingredients. The time complexity of such an approach would be O(R*I), where I is the average number of ingredients per recipe. This becomes highly inefficient as the number of recipes and ingredients grows. By contrast, the optimized approach leverages a graph structure in topological sorting to achieve O(V) plus E complexity. This significantly reduces unnecessary computations, making the solution much more scalable for large datasets where R, S, and E are substantial. To solidify our understanding, we can mathematically validate the big O complexity. The graph has V equals S plus R nodes, representing the supplies and recipes, and E edges, representing the ingredient recipe pairs. Constructing the graph requires iterating through the edges, resulting in O(E). The BFS traversal processes each node and edge at most once, giving a complexity of O(V) plus E. Combining these steps, the total time complexity is O(V) plus E. For space, the graph and queue dominate the memory usage, both requiring O(V) plus E. This analysis confirms that the solution is both time and space efficient, utilizing graph algorithms to minimize redundant computations and handle large-scale inputs effectively. When solving this problem, there are several common pitfalls to watch out for. First, not handling circular dependencies is a critical mistake. If a recipe indirectly depends on itself through other recipes, it can create infinite loops or incorrect results. To avoid this, you need to check for cycles in the dependency graph. Next, assuming that all ingredients will always be available or producible is another error. You must validate that every ingredient for a recipe can be either supplied initially or produced through other recipes. Inefficient graph traversal is another common issue. For instance, repeatedly verifying the same recipe can waste a lot of computation time. To solve this, use techniques like memoization or marking recipes as processed. Additionally, duplicate recipes in the input can lead to redundant or incorrect results, so ensure that recipes are uniquely identified during processing. Finally, building the graph incorrectly, such as reversing the direction of edges between recipes and ingredients, can lead to completely wrong outcomes, so double-check your graph construction process carefully. Now, let's explore some insights that are particularly useful for interviews. This problem is best modeled as a directed acyclic graph, or DAG, where nodes represent recipes or ingredients, and edges represent dependencies between them. Key operations here include topological sorting and graph traversals like DFS or BFS. At its core, this is a dependency resolution problem, similar to those you might encounter in build systems, project scheduling, or prerequisite resolution scenarios. To ensure efficiency, focus on reducing redundant computations by using memoization or marking nodes as visited during traversal. Lastly, always be prepared for edge cases. For example, you might encounter empty input, recipes with no ingredients, or graphs with circular dependencies. Being able to handle these scenarios gracefully is crucial for writing robust solutions. This problem shares similarities with several other well-known graph problems. For instance, LeetCode 207, course schedule, also involves dependency resolution, where you determine if all courses can be completed. Building on that, LeetCode 210, course schedule 2, extends the challenge by requiring you to return a valid order of course completion. Another related problem is LeetCode 802, find eventual safe states, which focuses on identifying nodes in a graph that do not lead to cycles. Finally, LeetCode 269, alien dictionary, offers a unique variation of topological sorting, where you determine the order of characters in an alien language based on given word dependencies. Exploring these problems can deepen your understanding of graph-based dependency resolution techniques. Now let's discuss some alternative approaches to solving this problem and the trade-offs involved. A brute force method simply iterates through all recipes and their dependencies, checking each one repeatedly. While this approach is easy to implement, it is computationally expensive, often resulting in O(n)(, or worse for large inputs with redundant checks. A more efficient solution involves using topological sorting, such as Kahn's algorithm or DFS, to determine the order in which recipes can be produced. This guarantees an optimal runtime of O(n plus E), where n is the number of nodes and E is the number of edges, though it does require careful graph construction. Another powerful approach is dynamic programming with memoization. By caching the results of recipes that have already been processed, you can avoid redundant computations and significantly improve runtime. However, this comes at the cost of slightly higher memory usage. Each approach has its trade-offs, so the best choice depends on the specific constraints and requirements of the problem at hand. Great job! To wrap up, we summarized the problem, the algorithm used, and its efficiency. We also highlighted when and why this solution works well. Thanks again for joining, and I'll see you in the next problem-solving session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!